So let's start with the another very important topic in GATE examination, that is power engineering. So in power engineering, we will deal with the steam nozzles, steam turbines, Rankine cycle and Brayton cycle. So let's start with power engineering. And in power engineering, we will discuss with steam nozzle, steam nozzles, we will discuss with steam turbine, we'll discuss with steam turbine, we'll discuss with Rankine cycle, or this is cycle for the steam power plant, steam power plant. Then we will discuss Brayton cycle, which is for gas turbine. It is for gas turbine. So in this topic that is called power engineering, we are interested in four things. So let's start with steam nozzle. So first of all, I am taking steam nozzle. So we have already aware with nozzle is a device which is used for getting high kinetic energy. So now I am defining the steam nozzle in an engineering manner. So the steam nozzle is a device where the enthalpy of steam is used to convert the heat energy, or enthalpy of the steam is converted into kinetic energy. So in other words, we can say that in steam nozzles, the enthalpy of steam is converted into kinetic energy. So I am again defining the steam nozzle is a device where the enthalpy of steam is converted into kinetic energy. So I will define steam nozzle. A steam nozzle is a device in which enthalpy of steam, or we can say that high enthalpy of steam is converted into kinetic energy. So basically, we are having two kinds of steam nozzle. So I am giving the classification of steam nozzle here. We are having two kinds of steam nozzle. First is convergent nozzle, and second one is convergent divergent nozzle. So I will show the diagram for convergent nozzle. The area of cross section will gradually decrease. It's a kind of convergent nozzle. Here the one section is inlet and two section is outlet. Similarly, in case of convergent divergent nozzle, we are having this kind of profile. So here we are having input section, here we are having output section, and here we are having a throat. You can say that this one is throat. Throat is nothing but a section where the area of cross section of the nozzle will be minimum. So this is a typical diagram for convergent nozzle and divergent nozzle. So here if you see that in convergent nozzle, the area of cross section is gradually decreasing. So we can say that if area of cross section is gradually decreasing, then definitely we will get the kinetic energy. But in case of convergent divergent nozzle, if you see at 2 dash, that is output of the nozzle, the area of cross section is increasing, but still it is working as a nozzle. So for this kind of consideration, when this device will act as a nozzle or when this device acts as a diffuser, means if you say one device is nozzle, it may be also acts as a diffuser. Diffuser means here the kinetic energy will decrease at the output, means we are getting the reverse effect. Suppose in nozzle we are getting the higher kinetic energy, that is a conversion of enthalpy to kinetic energy. So in diffuser we will see the kinetic energy will convert into entropy. So the most important parameter for such kind of discussion will be Mach number. So Mach number will decide either the device will behave as a nozzle or diffuser. So now I will define the term Mach number. Mach number. So now first of all define the term Mach number. The Mach number M, the Mach number M is defined as ratio of the actual velocity, ratio of the actual velocity v to the sonic velocity c, to the sonic sonic velocity c. So now I can define the Mach number. M is nothing but v by c. So this Mach number is very important here. So for for flow theory, if m is greater than 1, we are calling supersonic flow. If m is less than 1, it is calling subsonic flow. Subsonic flow. And if m equals to 1, it is calling sonic flow. So this one is a typical definition of Mach number. So now I am writing the one formula which will be very helpful in deciding the device which will act like a diffuser or nozzle. So I am writing a very important formula here, that is dA by A equals to m square minus 1 and dV by V. This is a very important formula which is used in compressible flow. Used in compressible flow. Compressible flow means where the density will vary. So it is used for compressible flow. So now I am giving one example here. Suppose I am taking a structure where the area of cross section is decreasing. That is suppose 1 section. That is suppose 2 and steam is entering here and going out. And suppose Mach number is less than 1. That is for subsonic flow. So now if I am using this thing dA by A m square minus 1 dV by V for this case, that is our example. So in that example, if you see Mach number is less than 1 negative, and here if you see the change in area means A2 minus A1 will be negative. So this thing will come negative here, and if you see this thing m square, that is coming less than 1, so again it will come negative. So here dV by V, so this dV, that is change in velocity, will come positive, means velocity is increasing, so it will act like a nozzle. So we can say that above device will act as a nozzle. So now let's take a second example here. I am drawing the device. I will draw the device here, same kind of device I am drawing. Here section is 1 here section is 2 Steam is entering here, steam is going out here. Suppose m is greater than 1, that is our supersonic flow. So now again we will use dA by A m square minus 1 dV by V. So here again area of cross section is decreasing, so dA will be negative. M square is greater than 1, so m square minus 1 will be positive. So dV by V, so definitely dV will be negative. Means kinetic energy is decreasing. So above device will act as a diffuser. So by this way we can easily decide whether the device will work like a nozzle or diffuser. Now I will talk about some of the important facts about nozzle, that is discharge through the nozzle and what will be the condition for its maximum value. So I will write discharge through the nozzle, discharge through the nozzle and condition for maximum value, maximum value. So remember one thing, whenever the nozzle will design, it will design for maximum discharge. So I will write nozzle will always designed for maximum discharge. So nozzle will always designed for maximum discharge, and for maximum discharge, for maximum discharge, it is called choke condition. It is called choke. For maximum discharge, it is called choke nozzle. Means we can say that the nozzle will always design for the maximum discharge, or we can say that ideally the nozzle is designed for choke condition where we will get the maximum discharge. So now I will write some of the formulas which are important for calculating discharge and the maximum discharge. So now I am writing the condition when the discharge will be maximum. So I am writing discharge through nozzle. Discharge through nozzle is maximum when critical pressure ratio critical pressure ratio. So now I will define critical pressure ratio, that is nothing but throat pressure divided by inlet pressure. Throat pressure divided by inlet pressure will be equal to 2 upon n plus 1 to the power n by n minus 1. So here n is nothing but the index of expansion. So I will write in terms of mathematics, throat pressure divided by inlet pressure equals to P2 by P1 equals to 2 by n plus 1 to the power n upon n minus 1. So remember this thing, that is for maximum discharge. That is the condition for maximum discharge. Now I will write the value of maximum discharge. So the value of maximum discharge maximum discharge is given by it is mx equals to a and p1 by v1 2 upon n plus 1 n plus 1 divided by n minus 1. So by this way we can easily calculate the maximum discharge. So now let's discuss about steam turbines. Steam turbines. So now I will define what is the meaning of steam turbine. So a steam turbine is a device in which enthalpy of steam is converted into kinetic energy. Means the difference between the nozzle and the turbine is that in nozzle also the enthalpy will convert into kinetic energy, but in steam turbine this enthalpy which is converted into kinetic energy, then it will convert into mechanical energy of rotation of turbine shaft. So I will write steam turbine is a device in which so steam turbine is a device enthalpy in which enthalpy of steam is converted into kinetic energy and then this kinetic energy used means, or we can say that this kinetic energy is converted into mechanical energy of rotation of the turbine shaft. So that is the basic difference between steam nozzles and steam turbines. So basically the steam turbines are two kinds of steam turbines. One is impulse turbine and second one is reaction turbine. So I am just classifying the steam turbine here. Steam turbine, one is impulse turbine and second one is reaction turbine. So in case of impulse turbine, the full enthalpy of the steam is converted into the kinetic energy in nozzle itself. Means there will be no change in enthalpy in rotation. But in case of reaction turbine, the enthalpy of the steam will also change in moving blades. So I can write no change in enthalpy of steam in rotor. Here change in enthalpy of steam in rotor. So that is the basic difference between impulse turbine and reaction turbine. So now I will give some of the examples for impulse turbine and reaction turbine. So whenever they will ask in GATE examination, so it will be very easy for you. So I will give the first turbine, that is the Hero's turbines. So I will write first turbine is Hero's turbine. Hero's reaction turbine. You can say that steam wheel. So the first turbine is the Hero's reaction steam wheel. And now we are having the single stage impulse turbine, that is called De turbine. So I can write single stage impulse turbine. Impulse turbine is also called De turbine. De turbine. So remember these two things. The first turbine was the Hero's reaction steam turbine, and the single stage impulse turbine is called De turbine. So now I will talk about in terms of compounding. So now I will talk about compounding of compounding turbine. So basically there are two kinds of compounding, that is velocity compounding and pressure compounding. Velocity compounding and second one is pressure compounding, and we are also having, that is combination of velocity and pressure. So I can write pressure velocity compounding. Pressure velocity compounding. So first of all I will talk about what is compounding and why it is necessary. So suppose we are having a high enthalpy of the steam, and now we are converting a high enthalpy of steam fully in a one nozzle, and this velocity is very high, and we are getting a very high speed of the turbine. But in practically, this turbine is useful for production of electricity. So there is a constraint in terms of rotation. Means we are having a high rotation, but our requirement is less rotation, so we will provide some kinds of gear arrangement. So we are wasting the some amount of kinetic energy by gearing arrangement. So that's why we are going for compounding. Means the whatever the kinetic energy or whatever the enthalpy is required in each steps we will use, and the remaining enthalpy we will use in the later stage, so that by this way we can utilize the full enthalpy or full kinetic energy of the steam for producing the electricity. So that's why we are having velocity compounding, pressure compounding, and pressure velocity compounding. It depends upon which kind of physical quantity we are taking for compounding point of view. So I will give the related example for velocity compounding turbine, pressure compounding turbine, and pressure velocity compounding turbine. So the velocity compounding turbine, I am having the turbine Curtis. So the Curtis turbine, is called the velocity compounding turbine. Similarly, for pressure compounding turbine, we are having RATEU, RATEAU. So the RATEU turbine, that is basically for pressure compounding, or we can say that RATEU turbine is the pressure compounding turbine. And now we are having the reaction turbine also. So I will talk about the reaction turbine. So the reaction turbine we have already discussed, in which the enthalpy will also change in rotor also. So we are having a very famous reaction turbine, that is Parsons turbine. Parsons turbine. So why I am giving these examples, because these examples are very important from gate point of view. So you can directly remember these things, and whenever they will ask, you can directly take the correct answer. Now let's take an important concept regarding steam turbine, that is velocity diagram. Velocity diagram. So I will just draw the velocity diagram for inlet and outlet, and then we will see how we can calculate the other things which are very important. So here I am taking the blade here, that is our moving blade. I'm just drawing the moving blade which is going with the velocity of Cv, that is velocity of blade, and I am putting Cv1. Here we are having the inlet, so I am drawing the velocity diagram for inlet here. This is the velocity diagram for inlet. I will first write whatever the things given, and then we will see the other things. So this one is Cw1, this one is C1 here, this one is Cr1, CFO. So now that is at outlet. We are having CRO, that is relative velocity. This angle is phi and this angle was alpha. Here it was theta. So phi here we draw. So this one is CB1, this one is CW0, that is at outlet. CO, one is CF1. So this is at inlet and outlet. I will write inlet velocity diagram. Velocity diagram. This one is outlet. Outlet velocity diagram. So you just remember how I draw the diagram and how I put different values here, and I have put all these values here. Now I will write what are the notation meaning here. I use the CV1 here, that is nothing but linear velocity of moving blade. So linear velocity of moving blade. So this one is just linear velocity of moving blade. So here I will represent this one is nothing but moving blade. Now we are having C1, that is absolute velocity of steam. Absolute velocity of steam. Entering into moving blade, or we can say that entering and moving blade. Similarly, we are having C naught, that is absolute velocity of steam leaving moving blade. Absolute velocity of steam leaving moving blade. Similarly, we are having CW1, that is velocity of wheel at the entrance of moving blade. At the entrance of moving blade. Or we can say that it's a tangential component of C1. Similarly, CW naught, that is velocity of wheel at exit of moving blade. So here I will mention this velocity of wheel is only the velocity component which is responsible for rotation. So it is very important for calculating force and power. Similarly, we are having CF1, that is velocity of flow at entrance of moving blade. Right? entrance of moving blade, moving blade. This entrance of moving blade. Similarly, we are having CFO, that is velocity of flow at exit of moving blade, moving blade. I will mention one thing here, that is velocity of flow is nothing but it is axial component. This one is axial component. So this axial component will put thrust on the turbine. So this is responsible for producing thrust on the turbine. So now I will define CR1, that is nothing but relative velocity of steam, relative velocity of steam at at moving blade at entrance. Similarly, I am having CR naught, that is relative velocity of steam at moving blade moving blade at exit at exit. And alpha is nothing but the angle with which the tangent of the wheel at which of steam with velocity c1 enters. So in other words, I will write that is nozzle angle. That is nozzle angle. Beta, here we can easily see this one is beta. So beta is nothing but angle which the discharging steam, will write angle which the discharging steam steam makes with the tangent of makes with the tangent of wheel at exit of moving blade at exit of moving blade. Theta equals to entrance angle of moving blade. Entrance angle of moving blade. Moving blade. And phi is the exit angle of moving blade. Moving blade. Now I will write some of the important formula. So I am writing here important formula which will be very helpful in solving the numerical problem. So let's take first formula, that is force on wheel. Force on the wheel. So force on the wheel we can calculate by this formula, ms dot Cw1 plus Cw0, that will be in Newton meter, and ms dot will be the mass flow rate. Similarly, here I can also calculate the power. Power per wheel will be ms dot as Cw1 plus Cw0 into Cv1, that is blade velocity, divided by 1000, so I will get in terms of kilowatt. Now let's take blade or diagram efficiency. So I am writing another important formula, that is blade or diagram efficiency So it is denoted by eta B1, and it is the formula for that is 2CB1 CW1 plus CW0 divided by C1 square. So remember this thing, this formula is very important, that is blade or diagram efficiency. The formula is twice of CB1, that is blade velocity, into velocity of whirl at inlet and outlet, the summation of that is CW1 plus CW0 divided by C1 square. Now we are interested in stage efficiency. Stage efficiency. So the stage efficiency is denoted by eta stage, and we are getting with this formula CB1 into CW1 plus CW0 divided by H1 minus H2, that is the change in enthalpy. So by this way we can get the stage efficiency. Now axial thrust, as I already told, the velocity of flow is responsible for axial thrust or axial force. We can say that axial force, or sometimes we can say that axial thrust. And if you remember the velocity diagram in which the direction of velocity of flow at inlet and outlet is opposite. So it's a vector quantity, so we have to take the difference of it. So ms dot cf1 minus cf0. By this way we can calculate the axial force or axial thrust. Now we are interested in energy converted to heat by blade friction, because whenever the steam is moving over the blade there will be a friction. Some of the energy will be wastage in overcoming friction. So now I am talking about energy converted into heat by blade friction, by blade friction. So that is nothing but loss of kinetic energy during flow. We can say that that is nothing but loss of kinetic energy during flow over blade. So we can calculate by ms dot cr1 square minus cr0 square. Here we have to take relative velocity. Now let's talk about optimal value of ratio of blade speed to steam. So now we are interested in optimum value of ratio of blade speed to steam. Blade speed to steam. We are interested in optimum value of blade speed to steam. So the optimum value is cos alpha by 2. We know the alpha is nozzle angle at the inlet. Now we are interested in blade efficiency. So the blade efficiency for two-stage turbine. Blade efficiency for two-stage turbine will be maximum when this ratio, that is optimal ratio, will be cos alpha by 4. At that time the blade efficiency for two-stage turbine will be maximum. In general, we can write the optimal blade speed. So in general optimum blade speed ratio for maximum blade efficiency or maximum work done or maximum work done is is given by optimal ratio equals to cos alpha divided by 2n. Now let's talk about degree of reaction. That is very important from that point of view. So now I will talk about degree of reaction. So I am writing what is the meaning of degree of reaction. So degree of reaction turbine is defined as the ratio of heat drop, or we can say that enthalpy drop over moving blades to the total heat drop to the total heat drop in the stage. So now I will again repeat, the degree of reaction is basically defined for reaction turbine only, because we know in impulse turbine there will be a no enthalpy or heat drop in moving blades. So basically the degree of reaction for impulse turbine will be 0. So now the degree of reaction turbine we can define as it is nothing but the ratio of heat drop or enthalpy drop over the moving blades to the total enthalpy drop. Now let's talk about the blade efficiency of reaction turbine. So now we are interested in blade efficiency of reaction turbine. Reaction turbine. So I am writing the formula here, that is blade efficiency of reaction turbine is nothing but 2 minus 2 upon 1 plus 2 rho cos alpha minus rho square. So this blade efficiency will be maximum when rho equals to cos alpha. When rho equals to cos alpha, and this maximum value of efficiency will be 2 cos square alpha divided by 1 plus cos square alpha. So now I will talk about the theoretical efficiency of reheat cycle. So now in the last I will talk about theoretical efficiency of reheat cycle. Reheat cycle. So it will be given by eta thermal equals to H1 minus H2 plus H3 minus H4, because here you will see the efficiency is nothing but work done divided by heat input. So here due to reheating we are having 2 work done, that is before reheating, that is H1 minus H2, and after reheating is 3 minus H4, and now it's divided by heat supplied. So that is the heat supplied before and after. So that's why we are having these two terms. So by this way we can easily calculate the efficiency of reheat cycle. So it was all about steam nozzles and steam turbines.